Hi again. Welcome back for the final and third video of this lecture. So we ended the last lecture by looking at some examples of variability and the impact it could have. Over here, we're going to consider confounding and other forms of bias. Without explaining the contents of the slide, I'm just going to give you a little bit of time to take a look and think about what you feel the take-home message is. So on the x-axis, we've got per capita expenditure on road maintenance, and on the y-axis, we've got the total US highway fatality rate. If you'd like a little bit more time, please just hit pause. So in this plot, we can see that there's a clear negative relationship between the two. And we might be tempted to conclude that as we spend more money on roads, the fatality rate decreases. However, that isn't what this plot is showing. This plot is showing that there's a clear negative association, but association does not imply causation. It doesn't mean that if we change the one variable, it impacts the other. And as humans, we tend to make causal statements, and we need to be guarded against that. So I've actually been a little bit dishonest about what's on the x-axis. The x-axis is actually showing the amount of fresh lemons imported to the USA from Mexico. When faced by this plot, it might be a little bit less tempting to draw that causal relationship. In another example of confounding, let's look at the delays in flights for two airlines. Suppose you were choosing whether to fly Continental or United. Based on the aggregate data, you would probably choose to fly United. 20% of United flights are delayed, versus 22.9% of Continental flights. However, when we look at this by city, we get a different solution. Looking within any city, one would now choose to fly Continental, which consistently has a lower percentage of flights delayed. This is an example of Simpson's paradox. This is when we see one association when we look at the data in aggregate, and we see a different association, possibly in the opposite direction, when we look within groups. Over here, city is a confounder. City is related to whether flights are delayed or not. So we have the most flights delayed in Newark and the lowest percentage of flights delayed in Detroit. City is also related to airline. So the majority of flights take off in the first city, whereas only about half of the United flights take off there. So city was related to each of our variables of interest, and that in turn was creating a particular relationship between them. For those of you familiar with logistic regression, here's the formal analysis of that data. In the top model, we have a logistic regression that does not account for confounders. This model produces an estimated odds ratio of 1.19, so that is the odds of having a flight delayed is 19% higher if we fly Continental rather than United. The bottom model includes the confounder city, and now the estimated odds ratio is less than 1. So the probability of a delay is lower using Continental rather than United. Now, even if we manage to control for all the confounders and get around all of the biases that we've already discussed, it still requires very thoughtful consideration when we think about what data says. And this is because it's easy to lie in statistics, unintentionally or intentionally. It might be deceiving the way data is presented, or we might introduce our own biases when we look at the presentation of results. Here's an example that speaks to that point. So suppose you were showing the scatter plot of data on two variables. What would you say is the relationship between them? I think for many of us, our reaction is that there isn't a relationship. It seems that the values of the variable on the y-axis stay the same regardless of the other variable. Let's add a little bit more detail to this plot. So this is actually a plot of temperature on the y-axis over time on the x-axis. So we're looking at how temperature changes over about 50 years. Based on our understanding of global warming, we now might expect a relationship. Let's hone in on the values on the y-axis. When we look at the data like this, we seem to see a clear signal. There's increasing temperature over time, and this is even after we take the variability into account by eye. So depending on what message we wanted to portray, we could choose to present a graph similar to this one or similar to the first one. So it's really easy to manipulate statistics through the way that we present data. This is just a fun little cartoon about this. So this is the very final example of this lecture. I'm going to present the data but not talk any more about it. In the summary and discussion, we can see what your thoughts are. This data shows the number of injuries that a cat experiences based on the number of stories that the cat falls. So each of these data points aggregates data from 10 cats, and the count of injuries is, for example, the number of bones that the cat breaks. So starting with a fall of 2 stories, the cat on average breaks less than 1 bone, and then the number of injuries increases. For about 7 stories, they almost 2.5 injuries per cat, and then it appears to drop again as we go to 9 floors. And researchers came up with an explanation for this. These results were published again in a credible journal, namely Nature. Over here, this researcher claims that as long as the cat experiences acceleration, the cat probably extends its limbs reflexly, but on reaching terminal velocity, it may relax and extend the limbs more horizontally in a flying squirrel fashion, thus not only reducing the velocity of the fall, but also absorbing the impact. Do you believe the explanation? To summarize this lecture, we use data to help form and revise models, and data are generally always better than anecdotes. Data collection should not be haphazard. It does matter how we collect our data, and with this we should also acknowledge that data are not easily obtained, especially good data. When working with data, be sure to consider the following factors. Think about how the data are collected. Consider whether there might be bias and other forms of confounding. Be aware that inevitably there's variability and that this can be misleading. And also think about how the data are analyzed and presented. In the end, as scientists, we want to be skeptical but also open. This need for balance between skepticism and openness is aptly captured by this quote by an American scientist. It seems to me what is called for is an exquisite balance between 2 conflicting needs. The most skeptical scrutiny of all hypotheses that are served up to us, and at the same time a great openness to new ideas. If you are only skeptical, then no new ideas make it through to you. On the other hand, if you are open to the point of gullibility and have not an ounce of skeptical sense in you, then you cannot distinguish the useful ideas from the worthless ones. That's where we're going to end this lecture. Thank you for your time, and I look forward to continuing the discussion.